Thank you, Homer. So, okay, heterogeneous resolution of commute time embedding features in Krylov subspaces is quite a mouthful, right? And for SVD and eigenvalue people, that may not have a lot of meaning. So the first thing that I want to do is sort of describe exactly what I mean by heterogeneous resolution and commute time distance. So the first thing is the context. What are the kinds of problems we're trying to solve here? And it's graph embeddings. A graph embedding is just a mapping from graph vertices to points in space such that the distance between vertex V and vertex U in the embedding has some sort of meaning. And for the commute time embedding, that meaning is the distance between V and U is the expected time it takes a random walker to get from V to U in the graph. And I just want to point out at this point that we're dealing with graphs which are undirected. These are not directed graphs. Although you may see later on in some of our definitions things which suggest directedness, there is no directedness here. Well, when you're dealing with spectral embeddings, and the commute time distance is in the class of spectral graph embeddings, you have to compute eigenvalues and eigenvectors, or singular values and singular vectors. And those are hard to compute, that's why we're all here. One of the things that graph mining people have done is they've taken the residual knob on their eigensolver and turned it up, way higher than you would typically do. We're not talking about machine precision, square root of machine precision. We're talking about much more relaxed residual tolerances. And when they do that, they found, well, we get data mining results which are pretty good. So we can get some compute time savings by relaxing our residual tolerances. That immediately begs the question, why can we get away with this? What are the salient parts and features of our approximate eigenvectors that come out of our relaxed solves that we need to do good data mining on our graphs? One of the observations that a colleague of mine, Jeff Sanders, I can't take credit for inventing the term heterogeneous resolution, Jeff invented that. But the notion is that particular geometric features of the embedding are going to emerge faster than others. So for this context, in the commute time context, we're interested in the long distance features in our commute time embedding. Okay, so let's look actually at an example of heterogeneous resolution, and I'll bring up this example graph which I've plotted in the first two dimensions of the commute time embedding. And we see that there's this, well-connected clump in the middle. This corresponds to 2009 college football network. So teams which played each other have an edge connecting them. And this corresponds to all of the FBS schools. These are the colleges with big athletic budgets and powerful football teams. And then we have these peripheral vertices, which are the FCS schools, on which we don't have any information about their season. So they end up being more peripheral. Now, the color map here, which you'll notice, just represents the distance from the origin to the vertex. So red is further from the origin and blue is right at the origin. Notice these colors when I show you the next plot of the resolution of this in a Krylov subspace approximation. And just before I go any further, I just want to point out that this isn't actually the commute time embedding. It's a projection of the commute time embedding. To show the commute time embedding, I need 159 dimensional screens, and due to budget cuts, I didn't get that, right? So we're going to have to deal with this two-dimensional screen. And now we can see, as we add dimensions to our Krylov subspace, the first two eigenvector approximations that we use for drawing the commute time embedding. At first, these red vertices and blue vertices are all scrambled together, but as we get higher dimensions, the red ones get pulled out away from the origin, and the blue ones get pushed into the origin. And by the time we hit, I'd say around 50 dimensions, we have a pretty good approximation. The long distances are pretty well preserved, but some of the shorter distances aren't so well preserved. And we can see that in a side-by-side comparison. See? We've got a little difference between our approximation and our actual commute time embedding here and here, but for the most part, the long distances are preserved. The red one, all the red vertices are pushed out towards the outside, and all the blue ones are pushed in towards the inside. All right, so now we have sort of a qualitative feel for what heterogeneous resolution looks like. Let's just throw up a couple of definitions of the matrices we're going to work with. We start out with, of course, our familiar Krylov subspace, powers of our matrix A times some start vector Z, which in our case is going to be randomly chosen. Even though we're going to deal with linear systems later in the talk, this is always going to be a random vector because we're going to be building a low-rank approximation to an operator. We have an adjacency matrix, which is just a mapping between vertex space and vertex space. I assume a mapping between vertices and natural numbers. We have a 1 in the VU entry of A, if V is adjacent to U and a 0 otherwise. We have a diagonal matrix with degrees of vertices on the diagonal. Those are fairly commonly used in spectral graph analysis, but this one is a little bit less frequently used, the oriented incidence matrix. This is a rectangular matrix which maps from edges to vertices. So we have a 1 if edge E is incident to vertex V, and a negative 1, what if it's on the negative end, the positive end? What does that mean, right? So we're dealing with undirected graphs. Well, the good news is you can just arbitrarily pick for any edge, one side of it to be positive and one side of it to be negative, and all the properties we need out of this oriented adjacency matrix hold. It's totally arbitrary. Now that we have the matrices we need defined, we can talk about these two interrelated concepts of commute time distance and graph PCA. These are due to Cerens and a bunch of other people, papers that were published around 2006. So the commute time distance is defined in terms of this combinatorial Laplacian, which is usually defined as the diagonal degree matrix minus the adjacency matrix. And the commute time distance takes this bilinear form where we take this, this distance between an element vector for vertex V and an element vector for vertex U, and we take the bidiagonal form of that vector on the pseudo-inverse of this matrix L. At this point we say, oh, pseudo-inverse, is this a well-posed problem? Well, the good news is that these right-hand sides are always orthogonal to the kernel of this matrix if the graph is connected, and we know that kernel a priori, so we can just set all of our iteration orthogonal to it. What I'm going to exploit here is that the combinatorial Laplacian is also the Gram matrix formed by our oriented incidence matrix, EG. So I can just solve it. I can turn my, my bilinear form into a least squares problem, and I can solve it this way. Now notice I'm also talking, when I talk about commute time distance, those of you who might already know a lot about commute time distance say, well, no, this isn't actually the commute time distance. This is a scaled version of it, because you'll to get true to commute time distance, you take this value and scale it by the volume of the graph, but for the purpose of ranking and ordering vertices, this is going to work just fine. Okay. Now, because we've noticed we're going to solve a lot of least squares problems, we don't want to do this with a big sparse graph. That's going to make us want to die. So we're going to try to find a reduced rank approximation to EG and do it with the SVD of our oriented incidence matrix. So we can just approximate EG with a low rank approximation based on these singular triplets with low singular values, right? And we throw out the trivial one that's in the kernel of L. Okay, so now I'm going to talk about how we're going to use commute time distance to cluster, and then sort of derive an ordering for all, these two sets which are going to be useful later. So if we think about the clustering problem of finding communities which are mutually well separated, this is kind of like co-clustering, but not exactly the same thing. Because really what we're looking for is almost like a bi-connectedness. We want well-separated well-separated clusters which you can only reach by going through like a centrally connected part of the graph. So we get these candidate clusters S1 and S2, which are of size less than m. We get their centroids, and then we get the distance between the centroids to build up our set S. And then what we're going to do is minimize over the set S, or rather maximize over the set S, the member which maximizes commute time distance. Now we're going to extract some subsets of S, F, and N, right? So think of F as far apart clusters, right? Clusters whose centroids are well separated. And N being clusters whose centroids are not so well separated. Then we're going to we want this property to hold, that well-separated ones are at least alpha further apart than not so well-separated ones. And we need this property to hold to be able to find the communities that we're looking for. Okay, so as I sort of had hinted at earlier, we want to find a low-rank approximation to EG so that we can compute commute time distance quickly. In fact, the structure of our approximation to EG is going to give us a lot of information about the vertices because it's going to be a commute time embedding. So instead of actually using graph PCA and calculating the proper SVD of our EG, we're just going to use all of the Ritz vectors that we get from a Krylov subspace. We're not going to throw out any of them. We're just going to take our Lanchos recurrence. Well, this is actually Lanchos recurrence you get from Golub-Kahan, not Lanchos, right? So you have two orthonormal matrices, Q and P, and a bidiagonal matrix, which you can QR factorize, and then you can build this low-rank approximation to our pseudo-inverse. And we want to know if I plug this low-rank approximation to EG into 2, am I still going to have this property holding? The strategy I'm going to go after in the rest of this talk is I'm going to try to show that right-hand sides, which are in F, are going to have error which shrinks faster than right-hand sides, which are in N. If I have that, then I know there's going to be some N, that is, some order of my Krylov subspace, such that the error here is going to be less than the error there. And that's going to guarantee that this property holds. So that's really the strategy I'm going to go after, and it turns out that in graph mining problems, there are particular properties of these right-hand sides which gives me that, right? So I'm going to be able to show the commute time distances of these well-separated centroids which are in my set F are going to shrink faster than right-hand sides which are in my set N. And here, the fine print which taketh away here is subject to this expansion of the right-hand side in the eigenvector basis of L, alternately the left singular vector basis of EG. And I'm just going to remember, okay, we're going to call our left singular vectors X, and we're going to order our singular values like this, with sigma naught being 0, and all of the others being strictly positive. Okay, and this is just sort of a more formal way of describing what I just said. Okay. The main idea in the proof is that these right-hand sides are going to pose an essentially low-rank problem. And we're going to see that in the proof sketch here. Right, so the first thing we do is we take our right-hand side and we expand it in our left singular vector basis. And we get these expansion coefficients Ci. But then we get some index k such that sigma k is the first singular value which is not less than 1. Now here's the key low-rank assumption that we're going to make. Right? We're going to assume that all expansion coefficients with index k or bigger are going to be trivial. Right? We're getting some tiny epsilon. And that the norm, so then we split our right-hand side BF into two pieces. A non-trivial part, and that's low rank, and a trivial part, which is the complement. And since the trivial part has all of these trivial coefficients, its norm is epsilon. It's orthogonal to our non-trivial low singular vector subspace. And we just go through the motions of our conjugate proofs of the convergence of conjugate gradient on the normal equations, except we choose a slightly different polynomial. It only has to be tiny in the interval between 0 and 1. It can grow up to 1 at sigma n, and we get convergence of the error, which looks like this. Okay, so for our well-separated right-hand sides which have a substantial low-rank part and a trivial complement, we get a much better condition number. Right? This condition number is much better than the general condition number of right-hand sides which are in our set N. What we give up for that is this sort of small positive constant. So we can have really good asymptotic convergence to epsilon squared. And as long as epsilon squared is tiny, then we're in good shape. Now at this point, somebody might notice and say, hey, wait a minute. Since you're exploiting this low-rank property of your right-hand sides, can't I just move the interval wherever I want? It doesn't really matter. It's just sort of arbitrary that the interval in which the singular values of singular vector expansion of this right-hand side, it's only arbitrary that it's between 0 and 1. I could move it to the right-hand side and have it be all on singular vectors which have large singular values. And that's absolutely true. So what we're going to see is that for short distance centroid pairs, we're going to have the same property hold. So let's look at an actual concrete example, because some of you may not believe that vectors, that right-hand sides are going to have expansions in this subspace. Now I sort of already went over this graph. We have this really well-connected part of FBS schools, and then we have FCS schools about which we have no information other than that they played some FBS schools. So, right, so we're going to have large commute time distances between them. We're going to enumerate all of the different pairwise commute time distances, and we're going to expand 3 of them, right? We're going to look at the closest, the ones which are the shortest commute time distance pair, the longest commute time distance pair, and the median commute time distance pair. And these coefficients here are sort of remarkable. Now I want to point out that here are the coefficients on the right, on the y-axis. The x-axis is singular vector index because it makes for nicer scatter plots. The value of k, where we go from singular values less than 1 to greater than 1, is right here around 50. So we can see that this long distance pair, FCS schools, which don't play each other, all the expansion coefficients are packed exactly where we expect them to be. The short distance ones, 2 FBS schools, which play each other, exactly the mirror image. And this one, FBS school, and an FCS school, which don't play each other, the expansion coefficients are all over the place. And we form a low rank approximation to EG, and we see exactly the asymptotic convergence that the theory would predict. The median one converges slower than the shortest and the longest. Right? Well, this is good for just computing, pairs, but nobody's going to do that to cluster. So I'm going to try solving a sparse PCA problem to try to find a B, which hopefully is in our set F. Right? So I have my Rally quotient here. I add a penalty to encourage sparsity. Sparse PCA is not really the same as robust PCA, and it's more similar to lasso. So I'm going to solve this equation using my Krylov subspace, not graph PCA. And that's going to allow me to solve it much quicker and more efficiently, but I hope that my commute time distance structure is going to give me the same answer. So let's look at solving this equation with a regularization factor of 1 in the full dimensional operator and the reduced dimensional Krylov subspace operator of dimension 60. We get exactly the same results. Well, that's good, but what do the results mean? We're finding exactly what we expect to find. Look at all these schools. They're all FCS schools. Exactly the kinds of members of that graph which are going to have long commute time distances between each other, because you can only get from one of these guys to another one of these guys by going through the tight interconnected FBS neighborhood in the middle. So let's just get to the conclusions, all right? This heterogeneous resolution is going to happen in other spaces too. This one just admitted the most convenient analysis, which is why I presented it to you here. We can do it also embedding in normalized Laplacian spaces. That's a different Laplacian operator. It's useful for finding different structure and graphs. It also has a kernel which is known a priori, just the same as a combinatorial Laplacian, but we may not have the nice properties of the orthogonality of the right-hand sides. Eigenvectors of graph adjacency matrices are also going to have properties like this, and that's interesting because graph adjacency matrices exhibit even more, they exhibit a high degree of eigenvalue clustering too. So we hope to find low rank problems embedded in those spaces as well. Linear discriminant analysis is another one. In case you're not familiar with that, that's just a method to find the best linear separator of two normally distributed classes. And then ordinary PCA, we're going to see that too, although any proof of this would look slightly different for ordinary PCA because we're not actually solving any linear systems. Now at this point, I just want to notice the dirty little trick I used to get here, and that is we have these special low rank problems embedded in high rank spaces. I mean, that's going to happen a lot in data mining, but in general, we're not going to see that. However, I think for particular kinds of data mining problems, or also for more general, in the more general case, we can still show heterogeneous resolution. We're just restricted to much messier theory, and that's the thing which I'm going to be working on next. So at that point, I want to conclude my talk and just ask if anybody has any questions.
Questions? Yeah.
So in the previous slides, you showed that long distance and short distance and medium distance, right? So how the singular value corresponding to the distance? So for example, for the long distance, the small cell matches the singular value corresponding to the other one, or?
Okay, yeah, so for long distances, since your commute time distance is going to, let me just sort of pull up this expansion, even though this isn't directly the quantity we're going to look at. It's because, the equation, this, the value it gives you commute time distance is just going to be this expansion, but just replace, this polynomial with the function which gives you, the reciprocal of the singular value. So the small singular values are going to contribute most to long commute time distances. Singular values greater than 1 are going to be contributing to short commute time distances. In fact, the bigger the singular value, the more it's going to contribute to having no commute time distance at all, right? So, as your singular values grow towards infinity, they're going to, converge towards vertex pairs which are, on top of each other.
Yeah, Alex, is there going to be much effect in sorting all these out and finding your differences by degree distribution on the graph? The graph you were using, all the nodes have the same degree, or very close to it. If you were to throw this technique at a scale-free graph, is it going to be harder, easier? What's going to be the effect of degree distribution, if any?
Yeah, so I tried working on a slightly larger graph which had more scale-free properties. And what I ended up seeing is that I didn't have, these really convenient eigenvector expansions. But the thing that I would claim is going to rescue you. So you're going to see large expansion coefficients here. But the thing I think that's going to rescue you is because most of those singular values are going to be really large. It doesn't really. You can apply a subspace filter that's just going to filter out all of those singular values and just work in this low rank space anyway. So since those since those large singular values are going to just contribute like epsilon to your commute time distance, you can just effectively ignore them. So I would, in that case, I would just project into this low rank space anyway. And okay.
Well, let's thank the speaker again.